We introduced Fiducial Exoskeletons, image-centric robot state estimation to enable simple and robust 3D robot state estimation, including robot camera pose and joint state recovery, robustly from a single image. Often in robotics, and especially in 3D robotic setups, we have to estimate the robot camera pose and the 3D position of each robot link. However, these are functions of highly precise and calibrated motors, and are generally cumbersome and challenging to obtain accurately. The video below illustrates the current way to obtain even just the robot camera pose estimate. A user tapes a fiducial marker onto the robot, moves the robot iteratively to roughly 5 positions, performs an optimization to recover the camera pose. Then their friend bumps into the camera, moving it, and the user frustratedly gives up on needing the robot camera pose. Note this is not only a clunky and cumbersome pipeline, but also depends on highly precise and calibrated motors. Today, we present a simple, image-centric robot's 3D state reformulation. In contrast, our method enables accurate robot camera pose and joint state estimates robustly from a single image. Here's how it works. We first install a 3D printed mount on each link with a fiducial marker. Then inference. Given a single RGB image, we estimate the 6D pose of each link, shown here in red. This is an incredibly rich source of information for the 3D robot state. Note the robot camera pose is already obtained here, as we estimated the 6D pose of the robot base, which is the robot camera pose we are interested in. Next, to recover the joint angles of the robot, we just perform a tiny real-time optimization over the joints to match the observed link poses. Here we show some casually captured state estimation results for both camera pose estimation and joint angles estimation from an uncalibrated iPhone camera, not using any motor information. Note that the robot is not even plugged in. You can see the cord dangling to the left of the robot. On the left, we show an example where the camera is moving and the robot is static. From leftmost to rightmost panel, we show the raw RGB stream, the simulator robot state, and the estimated camera position as a white plane, and the rendered robot overlay onto the RGB robot stream on the rightmost plane, showing that the estimation is tight. On the right, we show a video where the robot is moving and the camera and robot base is mostly fixed, but still moves a little bit because the base is not clamped down. Note how we can obtain the joint angles and 3D position of each robot link without using the motor information at all. Lastly, we also have some demos on improving control using our vision-based robot state estimation on a really cheap $100 robot. On the top left, we show the comparison of naively executing the target position overlaid in gray on the cheap robot, and on the right with our vision-based control loop, which is much tighter. On the bottom, we show a simple demo on a slightly more precise $300 robot, where an analytical grasp position on a known object is computed and the robot executes it. On the leftmost panel, we have the RGB stream with the pose estimations visualized. The middle shows the target robot grasp position in white and the detected link poses in red. And on the rightmost panel, we overlay the rendered target grasp onto the RGB stream.